All right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at Lewis dot structures. Now, Lewis dot structures are used to show the location of valence electrons in a molecule, and when we combine it with VSEPR theory, it can actually be a very powerful tool for predicting molecular geometry, bond angles, bond orders, relative bond lengths, resonance structures, hybridization of the central atom, and also the presence of dipole moments. So you can see that this is a very important tool for us, right? And we can also use formal charge to differentiate between possible Lewis dot structures. And then we can also use the Lewis dot structures to draw structural isomers to justify differences in properties between compounds with the same chemical formula. So before we get started, I think it's very, very important to frame the context of this lecture and let you understand, like, molecules are three-dimensional structures. They exist in interact in three-dimension, and so understanding their three-dimensional shape gives us a powerful tool to help us to predict and justify these interactions or these differences in properties that we'll see between molecules. All right, so what I've got on the screen now is actually just our quick and dirty rules, and I'm going to run through these really quickly. And we use these to draw Lewis dot structures just in the heat of the moment. We've got to get done. We got to go fast. And we see that our particular structure or skeletal structure that we're going to draw contains all these elements. Right? So hydrogen, the first one, it's just going to have a single bond. It's never going to have lone pairs, right? So it'll never have an octet, and it'll never be a central atom. The second, carbon, it will always have 4 bonds, and it will hardly ever in this class, you can actually just assume it'll never have lone pairs. And the other catch to that is that if it is present, it's probably going to be a central atom. Nitrogen is going to have 3 bonds and a single lone pair on the nitrogen. Oxygen, 2 bonds and 2 lone pairs. Halogens, this is fluorine, chlorine, iodine, right? That group 7A will always have 1 bond and 3 lone pairs. Now, this does have an exception because when it's a central atom, you actually have to use TiBo to draw the structure because it's not going to follow that particular rule, right? And then boron, our very last one, as a central atom, it'll have 3 bonds and no lone pairs. And so you can see boron, I always use the phrase, it's pretty crude, but boron's a moron. It's too stupid to have an octet. So as a central atom, boron will not have an octet. And so what we see is that if we can find and look at our structure that we're trying to draw, if it just contains a mixture of these elements, we can use these rules and just very quickly go about our business. Now, the issue arises when, what if we have something that's not in this list? What do we do? Well, in that particular case, we're going to use something called TiBo. And so if you take a look in the top right-hand corner, I've got just really quickly drawn out what TiBo is, right? And TiBo is just a tool that we use to draw Lewis dot structures. The T stands for total valence electrons. The B is our electrons involved in these sigma bonds. And a sigma bond is just a single bond. The O, this is the electrons and the lone pairs that I'm going to use to complete the octet of all of my outer atoms, right? And remember, a lone pair is 2 electrons. And then what I'm going to do is you'll notice I've got this T minus B minus O. If I have a remainder after that point, right, those are actually going to exist as lone pairs on the central atom. So I'm going to run really quickly through some examples with you. The first is going to be CH4. And I know these elements here, you'll say, hey, Mr. Doolin, these are part of our quick and dirty rules, and that's true, but I'm just using it to show you how to use TiBo, right? So my total in this particular case is actually going to be 8. My bonding, I'll pick one. The carbon is going to be my central atom. Hydrogens are going to be outer. So this single bond that I've got drawn, I've got 4 of them. Those are my bonds or my electrons involved in sigma bonds. And so remember, each line here represents 2 electrons. So I've got 2, 4, 6, 8. Right? Outer, remember, my hydrogens are always just going to have 1 bond and no lone pairs. So that's going to be 0. I don't have any remainders. Right? And so then I understand that carbon's not going to have lone pairs. It follows my rule. Right? The next one that we'll do will be NH3, and again, I understand. This is part of my quick and dirty 6, right? That I can actually just use those rules to write it, but again, we're going to show you TiBo with it. So my total in this particular case, again, is going to be 8. Draw out my nitrogen as my central atom to attach the hydrogens to it, and so I would have 6 bonds, or 6 electrons involved in these sigma bonds here, because I've got 3 bonds times 2. And then my outer, again, is going to be 0, so this time I've got a remainder, and remember, the remainder is going to go on the central atom down as a lone pair. The last one that I'll do with you is actually SO3. So SO3, sulfur has 6 valence electrons, oxygen has 6 times 3, so I've got 24 total. Again, I'm going to put 6 in sigma bonds to attach these oxygens, and then my outer, I do need to fill my octets of my oxygens. They get 6 electrons or 3 lone pairs, so that would be 2, 4, 6, 8, 10, 12, 14, 16, 18, and then I've got none left over. So sulfur doesn't have any lone pairs on it. And then also with this, I have to understand, I have to always look back at this central atom and make sure it has an octet, and if it doesn't, I'm going to remove a lone pair from an outer atom and put it into a pi bond or a double bond. And so I've placed all my electrons here, sulfur has an octet, and I'm done. And so again, you can see that TIBO is really just a tool that we use to place electrons in a Lewis dot structure. It's not the end-all be-all. If you're outside of Mr. Doolin's class, you've probably never heard of TIBO before, because every teacher has their own little tool and trick that they use to draw Lewis dot structures, and this is mine. And so again, I'm going to stress in this particular case, we had our 6 quick and dirty rules. If you only have elements like in the first two, we have carbon and hydrogen. I know that both of those elements are part of my dirty 6. Here I've got, in the second one, NH3, I've got nitrogen and hydrogen. Again, those are part of my dirty 6. And then here in the last one, I've got sulfur and oxygen. Well, sulfur is not part of the dirty 6, but oxygen is. And so I would have to use TIBO for sure to draw this last structure. I could probably get away with the first two using my quick and dirty rules, right? And the understanding is the quick and dirty rules are going to allow you to do this faster because it does take time to do TIBO. So a common question that pops up when we were looking at the SO3 molecule, and I've just redrawn it here, is something called resonance. Well, if you looked at that and really took to heart, you could have said, well, Mr. Doolin, you put the double bond over here on the right-hand side, but could it technically have gone on the bottom, or could it have gone on the left-hand side? And the answer is yes. We have 3 different places that we can put that double bond, and so what we have here is called resonance, which means we have a Lewis dot structure. We have more than one Lewis dot structure that can be drawn to accurately represent the particular molecule. And the dirty trick for, again, how to recognize this very quickly when you draw out a structure, I had a choice where I could put that double bond, right? So if your double bond can be put in more than one place, and not all of them, right, but it only goes in one place and I can put it in more than one place, then you have to understand we're going to have resonance, and what they're going to ask you to do is for you to draw all of your resonance structures. Well, it's not that difficult. Once you get it drawn, all you're doing is you're drawing the structure over again, but you're moving that double bond where it goes. So you'll notice the second one is a resonance structure, right? But all I've done is I've moved the double bond down to the bottom, and then we can do it again, and I would have the double bond over here on the left-hand side this time. And so those are the 3 resonance structures that occur with that sulfur trioxide. And it's very important for you to understand, ladies and gentlemen, that if you're drawing out these Lewis dot structures and you have to be able to recognize that something has a resonance structure, and you're going to have to just automatically learn to draw them out. Because just drawing this one over here on the left, like we did on the first page, does not accurately represent where the valence electrons are at. And that's what Lewis dot structures are designed to do. So if it has resonance, you have to draw it. All right, so the next thing we're going to take a look at is formal charge. So formal charge, again, related to Lewis dot structures, because what we're going to do is that sometimes we have a choice about where we're going to put bonds and how we're going to arrange things. So technically more than one Lewis dot structure can be drawn. The most common example that we run across, and you've probably seen this before, is when we draw carbon dioxide, you'll see that we have distributed these pi bonds, or these double bonds, equally across the carbon. Well, a lot of people will ask, well, Mr. Doolin, how come we can't actually have this scenario where we've got a triple bond and a single bond? And I always just told kids, hey, we just want to distribute the electrons equally, right? If there's symmetry that can exist, it probably does. But now what we're going to do is we're going to learn exactly how we determine that this Lewis dot structure on the right probably doesn't exist, and the Lewis dot structure on the left does. And formal charge allows us to distinguish and predict which one of these is most likely. So to calculate formal charge, we're just going to take the number of valence electrons for each element, and we're going to subtract out the lone pairs associated with it, and take the bonding electrons divided by 2. And the keys here, a formal charge of 0 is a good thing. A formal charge of a 0 is a good thing. If you have negatives and positives in your structure, what you're looking for is is the electronegativity of that element making sense with regards to the charge that it has? So a highly electronegative element like oxygen shouldn't be carrying a positive charge. And if it is, you're running into problems with that Lewis dot structure because oxygen's more of an electron taker because of its electronegativity, not the other way around. If it had a positive charge, it would be looked upon as an electron giver, right? It would be donating electrons to somebody else. And we know that oxygen does not do that. So really quickly, I'm just going to do carbon here. If I look, I've got 1, 2, 3, 4 bonds, right? Carbon has 4 valence electrons, and then in here it doesn't have any lone pairs, so that would be 0 plus, and it would be 4, actually it'd be 8, because it's bonding electrons divided by 2, and you'll see that that's 0, because it ends up being 4 minus 4 is equal to 0. And that's a good thing, right? Because again, remember, 0 is good. Now I'll come down here and I'll do oxygen. Well, oxygen has 6 valence electrons. Right here, it's got 4 lone pair electrons, plus it's got 2 bonds associated with it. So those are 4 bonding electrons divided by 2. So again, this is 4 plus 2 here equals 6, and 6 minus 6 is equal to 0. So we're still tracking along pretty good, and you'll see that this oxygen is identical to this one. So we're going to say that that formal charge calculation is good for both of those. Right? And so again, remember the saying here, 0 is a good thing with formal charge. Now we come over to the one on the right-hand side, right? Again, I'm going to look at carbon. Carbon is going to be 4 minus, and it's going to be 0 plus 8 divided by 2. And so my carbon is still 0, but the difference here starts to come in the form of the oxygens. So I look at this oxygen on the right, and we see that oxygen has 6 valence electrons. It's got 1, 2, 3, so it's got 2 lone pairs here, and then 6 bonding electrons divided by 2, and so we'll see that this is 6 minus 5, and we'll see that oxygen has a +1 formal charge. And now we're starting to think, uh-oh, there's a charge, and it's on oxygen, and it's positive. That's probably not a good thing. The next one we'll take a look at for oxygen, again, 6 valence electrons, minus it's got 2, 4, 6 lone pair electrons, and only 1 bonding pair, so 2 divided by 2, and so this one is actually equal to -1. So, because 6 plus 1 here is equal to 7, and 6 minus 7 is -1. Now, that's not necessarily a bad thing for oxygen, because if it was going to have a negative charge, right, we would expect oxygen to be the one carrying it. But now look, all of a sudden, rather than having zeros across the board like we did on the left-hand side, I start getting positives and negatives and zeros. And so if we're going to predict which one of these is more probable based on formal charge, we're going to say the structure on the left based on formal charge, because 0 is a good thing. And then the big drawback here is that I have an oxygen with a +1 formal charge. And the question becomes, well, how big can these formal charges become? Generally speaking, if you end up with a formal charge that's either bigger than +1 or smaller than -1. So we'll see our numbers for formal charges that we're really looking for is 0, +1, -1. If you end up with the +2 or -2, that structure is not going to work out because that formal charge is too large. So, all right, now that we understand how to draw Lewis dot structures, whether we're using the rules or we're using Thiebaud, we understand how to recognize when resonance occurs, and then we can use formal charge to distinguish between them. We can feel pretty good about drawing Lewis dot structures. The second thing that we're going to pair with Lewis dot structures is something that's called VSEPR. Now, you'll hear me say this in class. I pronounce it VSEPR just to be obnoxious, right? But VSEPR stands for valence shell electron pair repulsion theory. And what VSEPR does is it actually uses Coulombic repulsion between electron pairs around a central atom to predict a whole slew of things. So just using VSEPR and a Lewis dot structure, we can predict what our three-dimensional molecular geometry is. We can predict bond angles, bond orders. We can predict a relative bond length. We can predict dipole moments in the presence of them, and we can also predict hybridization. And so what we're going to do is we're going to run through all of these just really quickly, one by one. And so let's take a look at the first couple, molecular geometry, bond angles, and hybridization. Well, molecular geometry is just the three-dimensional shape name, right? So it's a name to describe the three-dimensional shape. The bond angles are actually the angles between my outer atoms. And hybridization, that really occurs when S and P orbitals are indistinguishable from each other while they're bonding. We understand that these Lewis dot structures all are encompassing the valence electrons, which are located in S and P orbitals. But what happens is when we get those orbitals involved in bonding, we can no longer distinguish between them, so we'll say that they've hybridized, right? But the big thing to understand is exactly what I've got written over here, that all of these are based on our AXE designations. So remember our AXE designations. This is going to give me, when I'm doing my Lewis dot structure, the A stands for the central atom, the X is outer atoms, and then the E would actually be lone pairs on the central atom. So this particular molecule would be an AX2 designation. I know the molecular geometry is linear. I know that the bond angle between these two is 180 degrees, and I know the hybridization here is sp because there's only 2 orbitals involved in this, right? And so what we're looking at here is we'll see that all just by drawing the Lewis dot structure and assigning an AXE, I can get bond angle, I can get molecular geometry, and I can get hybridization. Another example would be my AX3. So I've got AX3. Looking at this, I know the geometry is trigonal planar. I know that the bond angle in this is actually 120 degrees because of the AX3. That's the bond angle for AX3. And then I know the hybridization here is actually sp2 because I have 3 total orbitals that are actually being hybridized. So spp. Right? And then the last one that we're going to take a look at, a little bit more complicated here. So we'll see AX4, and I'm going to do a little bit crazy drawing here, right? Where now I've got some differences in what these lines are being drawn. I want to tell you what they are. A dark shaded line like this one means that this X is actually coming out of the page. A dashed line means that it's going into the page. So just this 2-dimensional drawing I'm using to represent a 3-dimensional structure, right? So the AXE designation here would be AX4, right? The geometry would be tetrahedral. The hybridization, since I have 4 orbitals to hybridize, would actually be sp3, right? And notice the exponents add up to how many bonds I need, how many bond positions I need to get hybridized. And then the angle on this would actually be 109 degrees. Right? And so again, all of that was based. As soon as I had the AXE designation, I knew exactly what the geometry, what the hybridization, and what the bond angles were. And so the next 2 things that we're going to take a look at on our list are bond order and bond length, right? So our bond order, this is going to be the difference of essentially how many bonding pairs of electrons are in my bond, and it's a combination of sigma bonds and pi bonds. Well, remember that and my bond orders are really just going to be 1, 2, or 3. So I'm going to do 3 examples down here, right, where I've got a carbon-carbon single bond, a carbon-carbon double bond, and a carbon-carbon triple bond. And so you'll see here, this represents a sigma bond. The first bond to connect 2 particular atoms is actually always a sigma bond. This carbon here, where a carbon-carbon double bond, I've got a sigma bond and a pi bond, and then down at the bottom I've got a sigma bond and then 2 pi bonds, right? And so my bond orders is what I'll do here. The bond order where there's just a single bond, the bond order is 1. Where there's a double bond, the bond order is 2. Where there's a triple bond, the bond order is 3. And again, it's all based on how many electron pairs are involved in that particular bond. So there's 1 pair here, 2 here, and 3 here. The next thing that we'll take a look at is bond length. And believe it or not, bond length can be associated with bond order. And so we'll look at the bond lengths of these. The bond length of a carbon-carbon single bond, a bond order of 1, would be 154 picometers. For a carbon-carbon double bond, it would be 133 picometers. And for a carbon-carbon triple bond, it would be 120 picometers. So you can see the trend here that as my bond order increases, my bond length decreases. So these 2 here, bond order and bond length, are inversely related, right? And the bond length decreases again because of the larger electrostatic attraction between the nuclei and those bonding electrons. There's more electrons that have an attraction to nuclei here, so the nuclei pull in closer together. So the last thing that's on our list that VSEPR is going to allow us to do is actually detect the presence of a dipole moment, right? And so really what we're looking for when we draw our Lewis dot structures is an asymmetrical distribution of electrons around a central atom. And so it becomes very important to start drawing and placing those lone pair electrons and the elements, the outer atoms, around that central atom appropriately so that we can actually find and locate and identify these dipole moments. So I've got 2 examples drawn here. I've got CH2Br2 and CBr4. Well, this one is actually going to end up looking just like this, where I've got the bromines on one side, versus CBr4, which is going to have the bromines symmetrically placed around that carbon central atom. And so we'll see here, just by drawing out these structures, I can identify that this particular compound will have a dipole moment, whereas this one will not, right? Because the bromines are symmetrically distributed around that central carbon in this right hand. This is going to be a nonpolar compound, and the CH2Br2 is going to have a slight dipole moment because now I'm electron heavy on one side of that carbon versus the other. And so if you're trying to find whether or not a particular compound has a dipole moment, a lot of the times what you're going to do is you're going to need to draw out the structure, look at the three-dimensional structure of the atom, and then you can actually detect and identify those dipole moments. So the next thing that we're going to do is we're going to take a look, and this is the very last thing, ladies and gents, so stick with me here. The last thing we're going to take a look at is what's called structural isomers. And so structural isomers are actually molecules with the same atoms present, but they're going to have a different molecular arrangement. And because they have a different molecular arrangement, we can actually have differences in properties, because maybe now we have hydrogen bonding, we have a dipole moment in one versus the other where we don't. We have greater LDF in one versus the other because of an arrangement. And so we start seeing these slight differences in properties that a lot of the times can be explained if we would just draw the structures out. And so I'm going to take a look at the left one here, the C2H6O on the left. I'll draw out this compound, and you'll see I've got a hydrocarbon left side, and so a relatively nonpolar chain over here, but then I come over to the other side, the right-hand side, and all of a sudden now I've got a dipole moment in the oxygen, and I've got a hydrogen covalently bonded to an oxygen, which means the IMFs present in this particular molecule would not only be LDF and dipole, but it would also have hydrogen bonding, right? And so we've identified that. Now I'll come over here to the one on the right-hand side, and we'll draw it just slightly different. I'm going to start out with the oxygen, and we're going to give me a carbon here and a carbon on the other side, and you'll notice all the atoms are the same. It's just a different arrangement. But in the one on the right-hand side, again, I've got a dipole moment with that oxygen. I've got LDF present, but I no longer have hydrogen bonding because I do not have a hydrogen that's covalently bonded to that oxygen. And so if I'm trying to compare properties between these two particular compounds, I'd look at the formula, and the formula would not give me any information because it's exactly the same. I'd actually have to draw the structures out, look at the structures, and say, all right, based on the arrangement, the Lewis dot structures here, I expect the molecule on the left-hand side to actually have stronger intermolecular forces because of the presence of hydrogen bonding. And the one on the right-hand side doesn't have that hydrogen that's covalently bonded to the oxygen, so there's no hydrogen bonding present, right? And again, we had to draw the structures to be able to identify the differences so that we could justify and explain the differences in properties. And so you'll kind of catch that as the main idea of this particular lecture, is that drawing a Lewis dot structure when we're trying to identify differences in properties becomes absolutely paramount. It gives us all this information just being able to properly draw the Lewis dot structure. Well, all right, ladies and gents, that's all for me. I know that was a ton of information. If you have any questions, I'll see you in tutorials for those. Otherwise, I will see you in class.